And now it is my pleasure to introduce our special guest speaker this evening. Skylar Tibbits is a trained architect, designer, computer scientist, and artist. And as director of the Self-Assembly Lab at MIT, his research focuses on developing programmable material technologies for our built environment. You're about to hear about 4D as opposed to 3D design, and it's really cool stuff. The students have already had a sneak peek, so for those that haven't heard his presentation, it's going to be fabulous. Skylar also teaches graduate and undergraduate design studios as a research scientist at MIT's Department of Architecture. He's worked at a number of renowned design offices, and he's designed and built large-scale installations at galleries all around the world. He also writes, and he's been published regularly in the New York Times, Wired Magazine, Nature, Fast Company, and many other journals. Skylar is also the founder of SJET, which I just learned was his initials, a multidisciplinary practice that includes architecture, design, sculpture, fabrication, and computer science. He also designs toys and robotics as well. He graduated from Philadelphia University with a Bachelor's of Architecture degree, and he minored in experimental computation. And he received his MS in Design Computation and Computer Science from MIT. So without further ado, let's all welcome Mr. Skylar Tibbits.
Let's see if we can pull this up. All right, thanks so much. Thanks for the invitation, STEM Institute. Thank you, everyone. And it was really a pleasure to talk to all the students before that. I think there was a nice engagement, and it was also interesting for me to look back at how I got here. And so part of what I want to do is describe how I got here, what we're doing, why we're interested in this super weird stuff, and why I called the research lab the Self-Assembly Lab. So as you heard, I direct the Self-Assembly Lab. We focus on self-assembly, obviously, and also programmable materials, and hopefully I can emphasize what that means and why it matters. But I came from a strange point. I came from a design background. I studied architecture, and then went to computer science at MIT and design computation. And there was a moment where code was influencing design, and code is still doing that. Computation has changed the game in many industries or every industry. And specifically in the design space, code has influenced what we can design, how we can design, and how we can imagine potential solutions that weren't possible before. In this image, you'll see many, many iterations. You can produce geometric complexity that was never possible before. You can evolve design solutions with genetic algorithms, etc. And then you can take those solutions and you can analyze them. You can simulate them both environmentally, mechanically, structurally, et cetera, you name it. So computation is changing what we can do. It's changing what we can invent. And that's not really anything new right now. This is a revolution that's happening, but we all probably have heard of it, and every industry has been influenced by it. Something that's slightly more new is how code influences machines and materials. And digital fabrication has produced this boom. MIT, I forget the exact date, was the first to connect a computer to a machine to make a CNC milling machine. And then that has boomed to, in this case, it's a 3D printer. You could replace that with a laser cutter, water jet, CNC router, you name it. So digital fabrication took a step further from code and design. It said code to machines can allow us to produce things that we couldn't produce before. And from that research, before I got to MIT, I was building these experimental structures and installations, et cetera, in different galleries. And it was this opportunity to say, I'm going to write my own tools. I'm going to generate code. I'm going to analyze the environment, analyze the situation, and produce structures that couldn't have been produced before conceptually. And then I'm going to communicate with machines and digital fabrication tools to physically produce those things. And so this is just one example of many. We did this for MIT's 150th anniversary, and it was looking at vaulted structures. So if you look at a cathedral, they have these vaults, but they're really difficult to build because you have to have complex formwork and lots of labor, et cetera. So we were producing these out of flat sheets, and as the seams line up, the curvature takes, the material takes the curvature, et cetera. So we're using code to generate these. But what I haven't shown you is that it took us lots and lots and lots of time to make these. This is me assembling a prototype for 6 hours straight, and it's pretty common, actually. If you look at manufacturing, construction, or even at a more maker movement, digital fabrication has made this a mandate, that we've all become slaves to our own projects in a way, that we can produce these super complex things, but we haven't been able to utilize computation as a way to construct things. And so what our research lab does is try to take code and not just use it as design, not just use it as machines, but use it as construction, so code for assembly. And we specifically work at macro scales, at large-scale industrial processes. And the topic of self-assembly is predominantly found today at nanoscales and microscales in synthetic biology, chemistry, material science, et cetera. And what we're trying to argue is that if you look at the industrial scale or these sectors, construction, manufacturing, infrastructure, products, distribution, there's a lot of energy that's put into these systems, a lot of man hours, fighting tolerances, trying to get better and better machines in order to force things together. And so what we're trying to argue is that the computational revolution can also influence the way we physically make things at the human scale. If you look at the other scales that I've been talking about, there's a revolution there happening as well. And mostly that revolution has to do with programmability. In synthetic biology, it's similar to genetic engineering in a way, but I look at those two in different ways. You compare genetic engineering in one way to sort of like breeding, that you manipulate the variables and you try to breed towards a successful outcome. Synthetic engineering is taking those fundamental components and trying to look at it like electrical engineering and building things from the components up computationally so that we can build structures we couldn't have ever built before. And then there's a field of DNA computing and smart materials, et cetera, at either slightly larger scales or still nanoscales. DNA computing is the ability for us to use DNA as a computational medium. So we use it like a hard drive. George Church at the Wyss Institute has actually demonstrated, he wrote a book, and then he encoded that entire book in DNA, and then he synthesized custom DNA with his book in it, and then he read his book out of DNA. So he showed that he could put his book into DNA as a hard drive. But people have also shown universal computing with DNA, and it's not just DNA. My favorite paper is billiard ball computing. So they showed billiard balls, like pool balls, can compute. And so then there was bubbles, and there's everything. And so we're finding out that everything can compute, and you can program everything from plastics to woods to objects to biology. And it's really just a frame of reference that if you can find a way to encode information, then you can see a program or you can embed a program and see behavior change out of it. Another example is this design revolution that's happening in DNA. There's a software called CAD Nano, and it's a CAD tool, just like AutoCAD or just like a 3D modeling tool. And what you do is you design 2D and 3D structures, and then it breaks it down into ACTG strands, and you order that. You can order it for $100, you get back these test tubes of DNA. And then you heat up the DNA, cool down the DNA, and you look at it, and the DNA has self-assembled into the structure that you designed. So what's fundamentally different about that is that you're not just designing structures and then sending it to a printer and hoping you get your final object out, right? You're designing structures and then you're encoding the blueprints in the materials themselves so that the materials assemble the structure. And that's a different mindset. And so what we try to do is demonstrate that at a much larger scale. One other example that's maybe useful is George Church also showed that you can build these drug delivery robots. He built on the bottom right a nano robot, all made out of DNA, designed in CAD Nano. It then functionally self-assembled into this capsule, and it only opens under specific conditions to release drugs. So the whole thing designed, fabricated, self-assembled using DNA. So at the industrial scale, most people would say, well, if we have automation, then we've solved our problem. If we just have smarter and smarter machines, then everything will be fixed. And although smart machines are really exciting and we're influenced by them, certainly, we also think that smarter materials have its place, and smarter materials can collaborate with machines and can collaborate with humans. And so what we're trying to do is find ways to make more elegant solutions for systems to assemble themselves, or at least error correct, or for the materials to respond to the environment and local neighbors, et cetera. So what does self-assembly mean? The definition is a process by which disordered parts build an ordered structure through only local interaction. So that means you have a bunch of parts. You don't need to pick up a part and find its neighbor and place the part like in a jigsaw puzzle, et cetera, but that I should be able to shake them, heat them, cool them, gravity tumble them, put them in water, and given the right conditions, those parts should be able to come together to build a precise structure. And that seems super crazy, but if you understand the biology space and chemistry space and physics, et cetera, if you're from those disciplines, you'll know that that process happens at many other scales except for the human scale. That in the human scale, we've become really, really good at building in a brute force way. We have sledgehammers, screwdrivers, materials, chainsaws, and we force stuff together based on our own desires and demands, and we forget about material properties, and we forget about all of these other energies around us. And so what we're trying to do is actually go back, in a way, to thinking about energy in the environment and material properties and how those can build precise things. So we've tried to break down the ingredients for self-assembly, and there's essentially three main categories. And the goal for this is that if you want to use self-assembly outside of, in biological context, or outside of scenarios where it exists today, how do we engineer that to make useful things? How do we know what to do to make stuff to self-assemble? So the top left is materials and geometry. This is essentially your components. Everything you build today is made out of materials, and it has a shape and functionality. That's kind of obvious, right? Everything we make has to have that. But then you try to design the interactions, and you try to say, how are these materials going to find one another? What happens when they hit one another? What are the material properties so they could stick or they could bounce off? How do they error correct? How do they find the right position or the wrong position? How much energy do they need, which is the third category. So energy, you could think about that by saying you need to get these things excited to go from point A to point B, right? You need to subject them to energy. And we're specifically interested in passive energies in the sense that we think there's abundant energies around us, frequencies and temperature and light and UV and all of these abundant energies that we can use and tap into to get things excited and make useful structures. We can also use electricity and fuels and all these other things too, but there is this abundant resource. Can you assemble things using sound is a good example. Why don't we do that? Why don't we build structures today using sound, which is theoretically possible? Can we use heat? Can we use moisture? All of these scenarios are what we're looking at. So one of the first demonstrations of pure self-assembly that we worked on was actually a collaboration with Autodesk and a molecular biologist, Arthur Olson. And we did this for TED Global 2012. We made a number of these glass flasks, and in each flask was a different molecular structure. So we had the poliovirus, a tobacco plant virus, enzymes, you name it. They had different numbers of parts, different geometric structures, and different colors. The number of components was demonstrating that you can build different types of things and that you can have different numbers of components that come together. The colors, as you'll see in a second, helps to demonstrate the stochastic process, that as you shake these things, they assemble in different ways, even though they lead to the final structure in the same way every time. So you take the flask, you shake it hard, and it breaks apart. And then you shake it a bit softer, but still randomly, and the parts come back together and self-assemble. And for us, this shows, number one, that you can use random energy to build non-random things. So normally people will talk about entropy and say structured objects move towards disorganization, or they break apart. And so what we're trying to do is design energy landscapes such that the parts, given noisy, free, random energy, can build useful, precise, non-random things. And the other thing it shows is that the user doesn't need to know anything about the system. That the user can pick up this flask, know nothing about the poliovirus, which this is in this case, know nothing about self-assembly, don't know anything about how much energy is needed, and within a few minutes, be really, really good at it, even though it's actually not them. And you find that if you close your eyes, you're actually better than if you try to jump in place. Because it needs this right amount of energy, and you'll quickly realize that too much will break, and there's a sweet spot. And once you're in that sweet spot, the parts will come together. Going back to the colors, we showed at Autodesk University that you could do chirality. You could do right-handedness and left-handedness. So we dump a bunch of black and yellow parts in the beaker. You shake it randomly, and you'll always get fully yellow and fully black. You'll never get half and half. You'll never get a soccer ball pattern or some mistakes. You'll always get it. You don't know exactly how long it'll take in any of these cases because it's a stochastic process. But you'll be able to separate. And the way we do that is through error correction. So the black and yellow parts can assemble in the wrong way, and they'll assemble upside down. But they're super weak. And then a third part can never assemble there, and they'll never bridge. So it'll always stay two, and they'll break and jump and break and jump. But then if two parts assemble in the right way, a third part will assemble, which makes it slightly stronger, and then stronger, and then stronger, leading towards successful structures and weeding out errors in the wrong structures. So we use this chirality principle as a way to ensure that successful structures are built, even though we're using this chaotic process. In 2012, we tried to show scalability. This was a project we did with Ted and again with Arthur Olson. And it started as, okay, what do we do as an installation for TED? And then we proposed, could we do an installation that produces installations? Instead of just a static installation, we essentially wanted to make a machine that made other things. And we called it the self-assembly line because we wanted to flip the assembly line. That in the assembly line, the user on the line knows everything about the parts. It's the skilled labor, it's understanding where the parts goes, and the materials are assumed to just be matter, and they're kind of dumb and they don't know what to do. And we force them in place. And we wanted to flip that, not saying that people are stupid, but that the people didn't have the information, and the parts had the information. And the people were just the energy. So we built this large rotating chamber, and we tried to demonstrate that you could assemble furniture structures. So we made a bunch of these furniture structures that would assemble inside the chamber. Again, they were based on the poliovirus. There's 12 components that make this dodecahedron structure. And the chamber rotates. People come up and they spin the chamber faster or slower, gaining this intuition about it. So as you spin the chamber, you start to understand, is this too much energy, not enough energy? Can I throw in parts that will block this? And a dialogue starts. People who don't know anything about self-assembly, don't know anything about design, don't know anything about what this is doing, start to collaborate and have a conversation. They say, okay, if this is the poliovirus, what could I throw into the chamber so that the poliovirus wouldn't assemble? How can I stop it from assembling? Which starts a conversation about drug delivery mechanisms. Or maybe a conversation about how we manufacture furniture pieces in the future. Or any industry you come from, there's this dialogue across disciplines. It's a topic that starts to span disciplines, and we can use it as a potential manufacturing or design solution. So in this chamber, we did the same thing as the flask, but at a much larger scale, and then we still have these furniture pieces in the lab today that we can sit on. And the time here took much longer than the flask. We're talking many, many minutes, maybe a half an hour even if you're starting to get super slow and tired. So in that sense, it maybe wasn't the best demonstration of efficiency for furniture. And I think we can obviously influence that by having more parts in the system and a number of other scenarios. But it was just this provocative solution. And in this case, we used art and an installation as a way to provoke possibility. Not that this is how we're going to make furniture, per se. Maybe we will. But that rather, we could do it. And it makes you think about how things come together at many different scales. In one of the presentations where I was showing this, I was assembling the structure backstage before I came back, or before I came on, and a different structure emerged. And it has never done that again. And it made this donut-shaped structure, where all the parts were in it. There was no errors, but it made a stable shape that was different than the shape we had designed. And that should be kind of obvious that there has to be some other scenarios that are also stable, maybe less likely, but also stable. And so then from that moment, we tried to design systems that could produce multiple outputs. if you think about a manufacturing solution, the previous examples I showed fit with that. You have a final product, you have a bunch of components, and you want to subject them to energy to make that final product. But there are other scenarios. You can think about a more designed solution that you may not know the best possible scenario, but you want a number of components that can be subject to energy to come up with a solution. And if you look at solid, liquid, gas, or you look at crystallization, it's that scenario where you have these fundamental components and they're subject to a certain type of energy and they rearrange themselves, called self-organization, into different phases. So the difference for me between self-assembly and self-organization is that self-organization can make many different structures. That you could make a solid-like structure, a gas-like structure, a liquid-like structure from the same fundamental components. We looked specifically at carbon. We had this tetrahedral shape with 2 positive, 2 negative poles, and we tried 1 and 3, 3 and 1, 4 and 4, and we could manipulate the system. And we were interested in structures like graphite, like diamond, linear chains, hexagons, pentagons, and trying to see what would emerge given these fundamental components and how do we design them so that they could hold the structure. We made 350 of these components. There's a bladder in the middle, and then an armature that holds 2 positive and 2 negative magnets, and then this whole thing is enclosed in another shell that holds water. And this allows it to be neutrally buoyant. So we have a 200-gallon tank of water, and we deposit 350 of these in the water, and you can see that they move freely in all 3 dimensions, which is a super strange thing to happen. Normally everything floats or sinks except for fish. And the moment that we did that, which is not that difficult to do, but it was like a really weird moment that these things are just hovering as if in outer space. And then we can program the pumps in the back and we can create different oscillations. So we can blast them to essentially increase the temperature so that everything breaks apart, or we can lower them so that everything moves towards a solid-like state, or we can create oscillations and chaotic patterns or regular patterns. So we can design the energy in the system so that certain structures emerge or break apart. If you look closely throughout this video, you'll see pentagons, hexagons, sometimes icosahedron-like structures. And so we're interested in both the local patterns and the global patterns. We're interested in those pentagons, hexagons, but we're also interested in how solids, liquids, and gases might emerge, or crystalline structures might emerge. And I think you can take this project in a few ways. Number one, you could say it's an educational tool. That if in every classroom around the world we had chambers that we could put physical, visual things in, and we could study existing principles, we could say, what is entropy? What happens with carbon? How much energy do I need? How do I change it, etc.? You would learn through these physical, dynamic, tangible devices. But then you could take it a step further and say, maybe we could discover new things. And because we can see it on a tangible human scale. Maybe I could understand and discover principles that I could have never seen at the nanoscale, etc., or the atomic scale. The last one, which I think is a bit more radical and provocative, is that we see this as the future of fabrication. That right now, if you take a printer, you send a file to a printer, you hope you get what you sent in. But normally you get kind of a crappy version of what you sent in, right? But it doesn't ever propose a solution that you didn't send in that would be better than your solution. So in the future, you could imagine you deposit materials and you give it some high-level goal. I want a furniture piece, for example, and I subject it to energy. And those materials then rearrange themselves into some optimal furniture piece given that energy, and you pull out this functional furniture piece, which is now a collaboration between you, the materials, and the energy that neither one or any could have produced alone, but that this fabrication materially self-reconfigures into solutions. So again, we're looking at the different scales, the global patterns, and we're now doing one in a 500-gallon tank. We have a 4-foot by 4-foot by 4-foot glass cube, and we're assembling lattice structures with the goal of pulling out fully stable materials. We're also doing floating ones. We have a 48-inch diameter fan that's blowing structures, and we're assembling them in the air. All different crazy scenarios of how can you assemble structures on their own when subject to ambient energies. So the other major category of research, so what I've just shown now is the self-assembly and self-organization work. The other major one is programmable materials. And we try to work with materials in a couple different configurations, linear chains and strands, or two-dimensional sheets, three-dimensional objects. And what we try to do is embed the capability for transformation, which we call 4D, meaning time, that things can transform, reconfigure, change shape, change appearance, change function, property, and we try to find ways to program materials to do that. I started this research as a graduate student at MIT. I've been there 6 years now, and there was the first year, and I started doing research with a professor named Neil Gershenfeld, and Neil Gershenfeld has a research lab called the Center for Bits and Atoms. And we had a DARPA program grant for programmable matter. And programmable matter was the Star Trek replicator vision, that if you had this machine, you could program the materials to change shape, to produce any material property, any shape you wanted instantly. But most of the people, and Neil, for example, were all looking at robotics. And so we took the robotic stance, but we said, instead of making smaller and smaller robots, can we make huge robots? Probably because of my architecture background. So we made these 12-foot long robot chains that could reconfigure sort of like a protein or like a snake into 2D sheets and 3D structures. And there were identical units connected together into this long chain. You could make as many as you want and assemble them on the end. And you sent in programs. So you could send in a program that would find the neighbors and tell one unit to go one direction, tell another unit to go another direction. The ultimate goal was that you could go from any one state to any other state, and that you could send in a high-level function, like, I want a cube. I don't care where you are, but get to a cube. And we never really got there. We got to the point where we could just say, Unit 3, turn right, go 120 degrees, Unit 2, go left, etc. But it brought up this question of programmability, and how do we scale programmability? And since that project, I've tried to go completely passive, that maybe robotics is not the way to scale super large scale programmable systems. First of all, they're super expensive, they're super failure prone, they last for about a week. If that robot lasted for a couple days. It's now my coffee table in my house. It has a nice piece of glass on top of it. But they're complex and they cost a lot of money and they fail often. But we still want the same functionality. We want this smart robotic system, but we wanted to take all the robots out. And so we did a lot of projects just on completely passive, like geometry, mechanical means, and some type of input energy. In this case, it's an infinitely reconfigurable line, or almost infinitely. So you can change this thing and click it into place in a million different ways. We did another one where you shake it randomly, and by shaking it randomly, it builds rigid structures. And so we're trying all these passive shapes that you could either sculpt or subject to energy, and programs could come out. And this one has recently turned into a public art commission for the city of Cambridge. So I'll play a quick video that shows how we scaled that up. So we're interested in producing this public art project that was reconfigurable, that every day you could go and you could see it in a different form, and that you could come up and you can change it and sculpt it the way you wanted, and that the community could shape their own. And it was under this solicitation for let the public play, meaning that not only kids play, but everyone wants to play, and people want to discover play through tangible interaction. And so in this case, the program wasn't when you play with it, it always produces the same thing, but that people could program it to do different things. So they can embed these simple codes of right, right, left, up, up, and it would provide a different sculpture every day. Another recent one we did for this recent TED, I'll show a video and explain it afterwards. So in this project, we looked at programmable materials based on shape memory effect. And what we can do is use temperature to anneal materials at a super high temperature so that when they're subject to a lower temperature, they'll automatically transform. And one of the nice things is that it's instant and it's totally repeatable. And it was a really simple commission to make these GIFs, simple cards essentially, but that it would allow people to interact with them and shape them and sculpt them however they want, and then program it so that it always returned to this spirograph design. And we made a number of different ones so people would open it and not know what the shape was going to transform it until they heated it up. And a lot of our work outside of what you've just seen has turned to printing. And printing is extremely hyped, and everyone here has probably heard about printing, and Obama talks about printing, and printing's this like thing that's going to save us and especially change manufacturing in the US. And we're super excited about printing, and we've used 3D printing probably for 10 years plus, and it's exciting, but I think Neil Gershenfeld again has a really good point on this. He says the 3D printer is like the microwave to cooking. We all thought the microwave was going to change cooking and that we wouldn't have a stove and we would only use the microwave. We all have microwaves, but we have other stuff too, right? And the microwave's great, but it doesn't do everything. And we think the same about printing. The 3D printing is great, but there are a lot of tools in a fab lab. And CNC routers, laser cutters, water jets, you name it. And traditional tools are all useful, and they all have different things. What we think is amazing about printing is not what everyone else thinks. We think the problems with printing are amazing. So on the right-hand side are all the challenges that 3D printing have. And I heard Michael Hayes from Boeing talk about the challenges of 3D printing, and he said, you know, these are some of the ones that we need to get over for us to actually adopt printing. One of them is bed size. And as printers get more accessible and cheaper, they get smaller and smaller and smaller, essentially making them less and less useful for most people, especially for large-scale manufacturing. And so there's a few takes on that. One would say, let's build huge printers. Let's build printers the size of buildings. And my perspective would be, if you want to build a skyscraper, you don't want to have to build a skyscraper-sized machine that makes the skyscraper, because you might as well stop at the machine. The second scenario is, let's build a farm of printers. And that's okay, but not everyone has a farm of printers. And if you want to build blocks from those farm of printers, you're probably going to be able to build blocks in a better way. And then you also have the assembly problem. So I'll show a project in a second that tries to reimagine how we could print really large-scale things from really small-scale printers. Second one is print time. They're super slow at the moment. There's a lot of exciting opportunities there. Software is a really new one, because for the first time in recent history, you're actually able to make things that you can't design for. If you think about almost every other moment, we could invent something that we had no idea how to make. But now you can make stuff that you don't know how to design, which is really weird. Our hardware tools have really challenged our software tools, and the software is trying to catch up again, because software was ahead of it for a while. And we're working with Autodesk on envisioning new software tools, and it may not even be what our software looks like today. What does software look like when you can program matter? It's a really interesting question for us. And the last two, I think, are the most important. That most people will say, well, printers can only do really bad versions of plastic, ceramics, and metals. And then we need printers to be better at those materials. And that's true. But what I think is more interesting is that we can now use printers as sort of a macro scale material science chamber. That we can make material compositions at a macro scale to perform in very precise ways, have multiple functions, contain programs, etc. That we can use these to make systems dynamic, transformative, reconfigurable. So this project we did for Ars Electronica, and we worked with the printer company Formlabs, which is a spin out of MIT. They make a low-cost, high-resolution SLA printer. And it's amazing, and it's the same price as a MakerBot, and you can make these super precise things. But the problem is that it's super small. You can only make 5 inches by 5 inches by 6 inches. And so we had a lot of fun, and we found all the things that you can't print. And we just put everything you can't print on top of it. Like almost everything. You can't print hardly anything. And so that was just hilarious to us. And then it spun out this project on what can we do to print really big things on small printers. And so we came up with this idea of taking a large object and then decomposing it, in this case in a chain, or some discrete number of things that are connected. You could do sheets, or you could do volumetric scenarios. And then we take that chain that describes the object and we pack it into the volume. So we basically just displace density. We put that super dense volume in the printer, and then we print it, the whole volume as dense as possible at the highest resolution that you can get. And that allows you to make this extremely long chain. In our case, we made a 50-foot long chain from 5 inches. And this long chain, not only from being radically long and having fun and dropping it off the side of the building in Austria, it demonstrates you can build large things, but you can also encode instructions in that chain. And I think that's the real capability, that same dense chain could encode the instructions for a chandelier in this case, or a furniture piece, or another functional product. That in the material itself, it clicks into place. And by clicking into place, it tells you, should I go right, should I go up, down, left, right, etc. And so the instructions are in the material and tell me how to make it, even if I don't know how to make it. And so it allows us to make these really large-scale things. We made a chandelier that was 8 times the volume of the bed. But actually, collaborators of ours called Nervous Systems, and they make jewelry, amazing stuff. It's generative jewelry, sort of computational based. I think did a better version of this. They took a dress, a full dress, and they crumpled it up like dirty laundry, and they printed that crumpled dirty laundry, and then they pull it out. Not only is it clean, but it's a full dress that you can wear with no assembly. And so they use this same technique of digitally folding and printing highly dense things into less dense, super large things. So I think that's a promising avenue for building large-scale things. But the one thing that all that didn't have is that it didn't assemble itself. It didn't do it. It just told me how to make it. It told me how to assemble it. And so then another interest of ours was trying to find ways that the material could transform literally. So we started working again with Autodesk, and this time with Stratasys. Stratasys is one of the leaders in the 3D printing space, specifically because they have the Connex line of printers. The Connex line of printers allows you to print multiple materials at the same time. So here you're seeing a time lapse of that. We're depositing, in this case, 2 materials. Now you can deposit 3, and you can guess that there's going to be many, many more. And you can deposit them extremely precisely in all 3 dimensions down to the droplet placement. So we're depositing a rigid plastic, which is the black that you see, and to me that's the braille. That's the geometric information that encodes a program or encodes something. And we use it as the structure, the backbone, the angles, the limiters, all the stuff that needs to tell us what to do. And then the other material is a expanding material, and that gives us the energy to go from one shape to another, and it expands 150% in water. So here you're seeing the red is representing that expanding material, and the white is representing the rigid material. And depending on the orientation, we can get different change. So if it's perpendicular to the plane, you get a fold in the plane. If it's parallel, you get a fold out of the plane. We can build precise angle transformation from any one angle to any other angle. We did a lot of calibration, both digitally and physically, to get any precise angle in all 3 dimensions. As I said, we're working with Autodesk, and the first thing is to show that we can simulate anything we can fabricate and fabricate anything we can simulate. So that takes a lot of empiric testing, and we've demonstrated those custom angles and larger structures. Almost anything you can imagine we're trying to simulate and fabricate. And then we want to turn the corner, and we want to say, can you optimize a solution for what we can produce, even if we don't know how to do it? Meaning, I want a cube, and I want to start from this shape, but I have no idea how to design this shape to get to a cube, and we want the software to be able to tell us that, and vice versa. We want to be able to say, go from any one shape to any other shape, or if I have this, what will I get, etc. One of the first demonstrations that we showed was a single line, and it has that white and black expanding and rigid material. When it's dipped in water, it transforms into the letters MIT. And here you're seeing an exploded view of all the stages in between. So we can program it specifically to go from a 1D shape into a 2D shape. And then we went further. We showed that we can print the letters MIT. And we can get the letters MIT to fold into the letters SAL. But it's a bit like abstract art. You have to kind of squint at it. And we'll help you in a second. We'll show it. And we were trying to show that you could go from a 2D shape to any other 2D shape and encode the folding in the shape itself. And we cheated a little bit. It's not the best. But we're trying. But we can go from one shape to another shape in 2 dimensions. And to demonstrate the custom angles, we started looking at proteins. That we could download a protein from the protein data bank. In this case, we downloaded the Crambin protein and just the backbone of it. And we break that protein down into a linear strand with all the custom angles of that structure. And so then we print that long strand, each having a joint that will allow it to go to the final precise shape of the protein. And again, we dip it in this convenient 250-gallon tank that we have. It's a good point to talk about temperature. So on all the previous examples, we're trying to get as hot of water as we can. The hotter the water, the faster it folds because it softens the black material. So on average, if you can get pretty hot water, it's about 15 minutes to fold, and those are all time lapses. This one, because of the water, took about an hour. It's hard to heat that much water, we found out. And we fold these things, and then we try to compare them, and we look at the structure and all the helices and all the angles, the precision of this structure compared to the original protein, and I'll show it in a second. And we're now interested in empirically testing the precision of it, but also what happens if we use these as an educational device again, that we could download any protein or any structure that we know of and print these to get a physical model, but also the dynamics of it and study how it tangles or study all the cross-linking or all the different components that we want to know about the protein. Can we study it visual, dynamic, tangible ways? Then we went into surfaces. So out of linear strands, you have 2-dimensional sheets. In this case, it's a flat sheet printed, again, with all of the joints that show the precise angles. And it folds eventually into a truncated octahedron. It's showing the precise angles of the surface to get to the octahedron shape. I think this one again points to this minimum volume, that if you can print flat sheets, you can minimize the time of producing an object and then let it transform on site. And you can also take advantage of shipping and minimize volume, et cetera. If you compared the time it would take to print the final structure versus the time it took to print the flat sheet and fold, the folding would win by far, not to mention the materials it would take to print the final object. I think a more elegant solution is this one looking at curved crease origami. So we take a flat sheet, and we have all the mountain and valley folds in the flat sheet, and we deposit that with the expanding material top and bottom. So when it's dipped in water, it takes a little bit of time, and then it jumps into place. And all of the forces have gone above a certain threshold to force the surface into this place. And you'll see in a second when I pull it out, it creates this hyperbolic structure with positive and negative curvature, and it has all of the precision of the mountains and valleys, but there's no joints or there's no added structure like we had in the other one. It's just about how much material and where do we place it to get this elegant fold. We then started to go into stretching. That if you want flat sheets to double curvature, you need stretching. Think about fabric, if you think about architectural panels, shoes, many products start out as flat sheets and you need to transform them into 3 dimensions. So if we can stretch a surface at every point along that surface in a very precise way, you can get the surface to transform in positive and negative curvature, extremely precise and extremely simple, just by these linear actuators, essentially. So you can stretch and shrink surfaces programmably across it. And this is the last example of the 4D printing stuff that I'll show. We rented out the Olympic swimming pool, and we printed a 50-foot long strand. I don't know why we like 50. It's a good number. And we folded this structure over the course of an hour. Again, they wouldn't let us change the temperature in the pool. And this structure folds 75 times its linear length. I think also pointing towards this educational model, you can imagine swimming next to proteins and studying how they fold, or macro scale applications, that we can fold really large scale things with fairly dynamic forces. We're now looking at how surfaces can be more continuous instead of discrete, and if we deposit continuous gradients, we can actually get different surfaces based on the time of interaction. So the middle one was 30 minutes, and the right one is 24 hours. So you can get very different structures based on how it interacts with the surface. So I'll show you one more project, again about programmable materials, and again about printing, but in this case, 2-dimensional printing. We were printing with DNA, and we worked again with Autodesk to develop a design tool that you could draw, you could import, you could make custom patterns and supply them with sequences of DNA. So they represent AAA, CCC, TTT, or some other sequence, and then simulate what happens if I wash with one sequence or another, so what patterns will show up. And you can imagine that if you have many sequences, this starts to get pretty complex. We then built some hardware tools to deposit it. It's basically just like your inkjet printer, but we're printing DNA. So we print this pattern on white paper, and then we wash with a complementary strand of DNA, and images show up, like in this case, MIT. So we're thinking about DNA as a magic ink, that you can start from one scenario that's sort of an abstract pattern and get to a slightly less abstract pattern that shows an abstract version of MIT. But the future is that you can use DNA, as I talked about in the beginning, with these as a computational material. That I can design a custom sequence of AAA, CCC, whatever it is. I can buy that, and I can design it to bind with something else, a protein from my skin, or another sequence of DNA, or some environmental influence. And if I print with that, then I get this magic ink scenario where you have a book and letters change based on who's holding it, or a signage that changes based on the sunlight or the pollution levels, or clothing inks in our clothes, or inks on our products that change based on its environment or its user. And so we look at this as a 2-dimensional programmable substrate. Okay, so where do I think all of this crazy stuff is going? for me, this image demonstrates where we are today and kind of where we want to go. That today we build super, super complex machines. You can look all around and they do amazing things, and they're made with complex parts. But the challenge is, how do those things come together? And one of the biggest hurdles in the production of those things is how we assemble them. And we either use humans to assemble them or really highly skilled machines to assemble them with lots of energy, fighting tolerances, et cetera. And we want to rethink how we assemble these really functional, amazing machines. And we think about it as a life cycle, that on the left-hand side, you have your products. And those products should be able to adapt to my demands. Those products should be able to adapt to the environment. So a good example is sportswear. Think about shoes. You have a different pair of shoes for everything you do. When you're walking, you want walking shoes. If I start running, they should become running shoes. If I'm on grass, they should grow cleats. If it starts raining, they should be waterproof. If the sun comes out, they should grow pores. Right? These products should adapt to me so that I can perform different and better, and they're responding to me, but they're also responding to the environment. And you could change that example with any other product, any other structure or mechanical means. Take anything that uses an actuator and a sensor today, and take those out and embed it directly in the materials itself. That we can create actuators and sensors and programs in materials to be smarter. So that points towards these materials that can be programmable, and we can jump on this revolution of smart materials, but we can actually customize them. We can make them from scratch. In manufacturing, that means that we want parts that can error correct and assemble themselves and communicate with us in machines to use abundant passive energy. Shipping, we talked about that in flat sheets that can transform. And disassembly is maybe one of the most interesting. You could say systems should be able to repair themselves. And we're working on these pipe prototypes that you can puncture them, and the secondary layer then expands and fills the gaps. You could say systems should be able to reconfigure themselves when they're not needed. Or more importantly, if we can self-assemble structures, we should be able to disassemble, self-disassemble for recyclability. I'll leave you with a quote that I think sums up the vision and the challenge. Can we design material parts with enough information and decision-making that they can assemble themselves and adapt independently to internal and external forces? And one last thing, I would invite everyone to reach out to us and try to collaborate or come visit us. We're more than excited to collaborate with people and students and a number of people from different disciplines, industry, government, academia, et cetera. So I'll leave you with that. Thanks so much.
It's fabulous.
So should I stay in the booth?
Yeah, if you could, that'd be great. So we do have some time for some questions, if anybody has a question for Skylar. Yes?
How durable the structures that you created in a 3D printer and put in hot water tanks?
So the question was, how durable are the systems that we've created? And I think the second question is, how scalable are these to be implemented in products today? So durability is a major challenge, and we're working closely with Stratasys. We work with their material science group, and we want durability on two ways. One, we want them to be able to last a long time in the traditional notion, and we're not there yet. So these will deteriorate over time based on many influences. And the second is that we want repeatability. So right now, if we deposit the materials in water, you take them out, they unfold. If you put them back in water, they fold, but that deteriorates quickly. And so we want it to be infinitely repeatable. That would be the dream. And the example of the red wire that tangled itself into this spirograph is instant and repeatable. And it will deteriorate, but much, much longer time. So I think that points towards it, although we didn't print that. So we want repeatability, but we also want some applications to be single directional. You could think about some type of safety mechanism that if it ever meets a condition, it closes or opens or changes, and it just stays like that. And it's either replaced or it's going to indicate that something happened. So sometimes you want one direction, sometimes you want two, but it's an ongoing process. And I think the reality is that every implementation is going to need different materials, it's going to need different functionality, and probably different ways to produce it. And printing may not be the way for everything. For the sportswear products, people are looking at printing, so it's a great fit. For other large-scale applications, we need to use lamination, injection molding, weaving, you name it. And I think we can do the same thing with different processes.
There's in the back. Yes, sorry.
You said about how do you store, I'm sorry, how do you store your coding into the material? And is it like a battery, or is it something, still the human interaction is required? So how do you create a self-sustaining system, or just to think into that line?
Yeah, so I think the program is two ways. It's geometric and it's based on material properties. So the Braille example is a way that you can encode a program or information in shape. So if I feel Braille, I can communicate or I can understand what was happening, et cetera. So we use geometry to program something. The other way is the material property, and a good example is the thermostat. If you take an old thermostat off your wall, there's a coil on the back, and it's a bimetallic strip. So two metals sandwiched together, and when the temperature increases very subtly, that coil turns to the right because one of those materials is expanding. When the temperature decreases, it turns to the left. So there's no motors, no electronics, no sensors, totally passive, responding to the environment in an instant way. And so for us, that's a material programmability, and then there's a geometric programmability. Some of them require humans in terms of shaking it or adding energy, et cetera. But we really try to separate that humans are good at certain things: abstract thinking, creativity, management, all of that kind of stuff. Materials are really good at physics and material properties and responding to energy and dynamics and things like that. And machines are really good at repeatability and precision and all those kind of things. So we try to use each one of the ingredients in a way that suits its best properties, let's say. Yeah.
Good question up here.
Yeah, so my question was, what are you guys working on right now? Like, what is your goal, your first step? Like, if they were to produce one thing, you know, to use on a common day-to-day basis, what are you guys aiming for there?
Yeah, I don't have a favorite application, but some of the first companies that approached us were the sportswear space, electrical and water infrastructure, medical applications, as I talked about, the software and printing space, and space itself, actually. Maybe the most exciting one for me is to be able to utilize these principles for building space structures. And I think it's going to be totally ironic if the first massive scale we build is actually, it's easier to build in space than it is to build on the Earth. It's like total shift. But one of the reasons for that is because of research funding. And in our home domain of construction and architecture, there's a real lack of innovation, a real lack of research funding, mostly because of litigation and building codes and all these problems. But space, defense, nanotech, materials, manufacturing, all have an investment in innovation. And so therefore, it's a lot easier to implement these technologies in those spaces.
Any question over here?
Okay, my question is, will the 4D printing be able to be sent from one place to another? I guess, for example, when you were talking about the dress, pack it down. So I wanted to let my sister buy a dress, I can pack it down and send it and she'll get it.
Yeah, and you could think about it in two ways. You could just send her a file, and then she could print the wrinkled dress and then pull it out. So that's one way. And so you don't have to send her anything. You just send digital information. But yeah, you could also use the kind of the compact nature of it to minimize the volume, so you pay less for FedEx, and then ship it and then pull out a dress that's like 20 times larger, and so FedEx will be super pissed because they didn't get their money. But yeah, you could do that too.
I read to know if you can use anything besides H2O as your transformation method, or have you ever used?
Yeah, we're interested in all forms. The red wire is actually heat. The water has nothing to do with it, but it's a really easy way to make uniform heat in a sense. Otherwise, we'd have to take a heat gun and go across it. So it's an easy way to get 200 Fahrenheit. But yeah, we've tried UV light. We've tried heat. We use water. We're interested in resonance and sound. We've used agitation, gravity. We're using air. Anything, you name it, and we're interested in doing it. Some are easier than others, but I think the wider that palette of activation energies, the more applicable.
Hi, you started your talk saying that, there's a lot of effort going on nanotechnology and nanomaterials. Did you envision yourself eventually getting your graphites into this big structure that would be self-assembly at the man scale?
I guess the question is how nanotech influences the things we can build at big scales? Okay, I see what you mean. So yeah, there's a lot of development at nanotech and synthetic biology and material science. Actually, in Europe, they opened this center for directed self-assembly. And so they're interested in using self-assembly to engineer materials that you couldn't have done through human or machine operations. And so therefore, we can get new materials, physical macro-scale material properties using self-assembly. But I think the bridge between those is really difficult. So you could do it hierarchically. You could say, let's use DNA origami to produce something that then produces something else, that then produces something else, and eventually gets up to my human scale. And that may be one way to go, and we collaborate with a lot of people in other domains. For now, what we've thought about is use these as a principle, and then be highly tuned into the materials and the energy at the scale we work at, and try to have similar principles make useful things. But I think the holy grail is that if you can make this seamless transition from nano to extremely macro, that's a really exciting but difficult challenge. And I think somehow we've become like incremental, that there's a lot of exciting developments at each stage, but we need to bridge them all. So yeah, it's the holy grail if we could do it. That one.
I have 2 questions. One is with the strand with the tank. I saw like it had a black and a yellow. Is the yellow with a different kind of force or a different magnetic identification? And then the other one is where the I guess the laser where it does the different strand and you take it apart. Will there be a way you can like expand that box, that volume into like a larger scale, or will that be more expensive?
So the first one was the black and yellow that you shake. How do we do that? So some of the first examples you saw, we use patterns of magnets to create that code. So in the yellow ones, it's like positive, negative, positive. In the black ones, it's negative, positive, negative. And that gives you a way to error correct. You don't have to necessarily use magnetics. You can use static, and you can use, material modulus of elasticity, and many other things. If you think about it in the kitchen when you're kind of sifting impurities out, or you're gold mining, because we all go gold mining all the time, you're shaking things and you're trying to get out impurities. It's a similar way. You're using gravity and filters in order to organize structures. So through random energy, things can either stay or fall, and you can do that with many processes. So in manufacturing, that happens a lot. So magnetics is one way to do it, but you could do others. The other question, I think, is how large can the printers be? Is that what you're saying? Yeah.
Okay, just as the other lady was saying, like how you can just pick it out of, unfolding the dress.
Okay.
Okay.
How big can you make it?
How big, or is there a possible way making a larger scale of that cubicle printing thing?
Yeah.
Is it
So.
expensive?
So great question. As you scale up, you lose density in a way, because we can't create any more theoretically. So you're printing here, and all the material has to be packed here. So you can build large structures, but you're losing something, and in that case, you're displacing the density. So there's some type of limit, but it depends on the application. If you need to build, a good example is in the space industry, they want to be able to take up raw materials and a single small machine, and be able to essentially just produce this material that then assembles into a scaffolding for solar arrays, or assembles into a scaffolding for an antenna. And so in those cases, it may not be about the density at every single point, but it may be about a larger structure that holds other things, et cetera. So for certain scenarios, I think it works, but there is a limit on how big you can get it. In terms of cost, printing is getting cheaper and cheaper and cheaper. What we're doing in terms of the 4D printing is the exact same cost as producing something that's 3D printed. Essentially, we're using 3D printers. The only thing we're doing is depositing multiple materials with different properties. And that allows us to get customizable smart materials, or essentially like printing robots that can transform on their own. It's not any more expensive. Yeah.
I noticed you use a lot of physical properties, such as magnetism and shrinkage. What are some of the, like, have you looked into things like chemical properties of things? For example, if you had like a goop made of, I don't know, different chemicals, and if you heated it to a certain temperature, these chemicals will react and form something like a bowl or something like that. Have you considered things like that?
We've considered it, but haven't done too much in that space. It's a great point. I guess the only thing that I guess my take on it is that I look at what we do as macro scale material science, that we're actually not inventing new materials, but that we're sandwiching or combining existing well-known abundant materials in such a way that they perform in functional ways. So a great example, we have colleagues in Stuttgart, Germany, and they take a linear strand of wood and they get it wet, and the linear strand of wood spells out their university. They wouldn't do MIT. But they use an existing, readily available, super cheap, theoretically super cheap, renewable resource as wood and program it in very precise ways by responding to the environment. So you can take that perspective, which is what we normally do because that's how we work with materials. So foams, plastics, metals, woods, we use those. Or you can take the perspective that you need to invent new materials and try to tap into their chemical property, et cetera. And we're interested in both. The chemical side of it is not normally our skill set, but it probably will expand into that space by collaborating with people.
My name is Joseph Warner from Alcento College, teaching chemistry at Skylar. It was excellent, and I think everybody enjoyed your presentation, and you evoked a great discussion. From the point of view of a chemist, okay, so why do you think, what is the advantage of all of this reassembling and self-assembling materials over what we already have in nature? For example, if you think about infected cells with HIV, okay, the virus is disassembling itself in the cell, and the cell is printing kind of new particles of the virus, and all this is, of course, coded in the RNA of the virus. So it is true that for each of these we need a separate printer, okay? So that's maybe one of the advantages, that here one printer can do everything in this. But how would you compare it? Because we already have all of those recombinant DNAs and genetic engineering. So all that information is actually assembled already or printed in the books, if you wish, right? And it can be used to regenerate virus or making new design proteins and everything. Of course, you cannot make this way new suit or dresses or shoes, but how you would think about it, comparing to, wouldn't it be easier to just copy Mother Nature, or is it cheaper, or?
Yeah, great.
If you can comment on this.
Yeah, great question. And there's a couple things there. One would be, I think the ribosome is a great example of where we might need to go. That not everything can be about autonomous parts that come together completely independently, but you need hierarchies. That the ribosome, as it's encoding and reading out, et cetera, is sort of like another level of it. That there's Brownian motion and there's a soup of parts, but then you also have these factories that are self-assembling other things. or at least encoding information for the protein to then fold. And so I think we need those hierarchies, that there may be larger scale structures that can produce more complex things, or you assemble at one scale and then you assemble those things into other scales to get more, I guess, universal functionality rather than demonstrations. So I totally agree with you there. The other perspective is, why not just use everyday things and reconstitute them in smarter ways? And that's one of the principles that we're really fond of, that, you know, if we can find these fundamental components that can assemble themselves or even be assembled easier, they could also be disassembled and then reassembled into other things. And in that case, I think it is recombining fundamental components. But you know, synthetic biology is probably much closer to what you're saying, that you use these fundamental components to produce structures that weren't produced before, but they're not inventing new components at that scale in a way. They're just using the system and the materials to produce new things. But yeah, I think the biomimetic stuff we were talking about previously, that we do try to mimic biology in some ways, but mostly through collaborations with biologists and chemists, et cetera. And extract principles, but rather be careful not to only make things look like biology, or only say we have to do it because biology works that way, because maybe there's other solutions that are better or equally good at another scale. Yeah.
We have time for one more question, and actually the young man in the gray shirt, there you go, right there.
So how might people need to change their home environments or their business environments to really capitalize on this kind of technology?
Yeah, great point. So I said before in the previous session that I look at our systems as cooking, baking, or gardening in a way, that maybe manufacturing can be much more like that, where you have these ingredients and you have energy and you don't necessarily know how the fundamental components are coming together, or you maybe don't need to know, but you need to give it the right environment and the right materials. Therefore, you can build precise things that you couldn't have built otherwise. So in that sense, I would argue that we don't need a revolution in the way our factories are today, or a revolution in the way our homes are today, et cetera. But rather, it's a more elegant relationship with materials and the environment. And so we have all these forces all around us anyway. There's an amazing paper that came out a couple months ago where scientists realized that they could throw Legos in a washing machine and they would assemble these structures. And then they tried to catalog all the structures that would assemble from their washing machine. And they were being kind of hilarious, but also I think pointing to the fact that we have machines that produce the types of energy that we need. We have abundant amounts of energy, and we just need to tap into them. Another interesting one, I had a student that proposed for his design project to do a natural disaster construction company. He was going to take landslides, avalanches, and earthquakes and construct useful communities and precise buildings out of it. And you know, it's far-fetched. That's not going to happen anytime soon, but it's a good point that there's these massive amounts of energy in tsunamis, avalanches, all the things, and if we can tailor them into functional, useful things, then it's a great resource that we haven't been using.